From the air, they look like metallic lakes spreading across the desert. Thousands of bright surfaces shimmer, tilt, and seem to flow around a tower glowing in the distance. But the surfaces are not liquid, and they are not ordinary solar panels. They are moving mirrors, each controlled by a computer, all working together as one enormous machine. Their most important job is not simply to make electricity while the sun is shining. It is to capture sunlight as heat, store that heat, and use it hours later. In other words, these strange desert fields are trying to make daylight wait until after dark. To see how that works, follow one beam of sunlight through a real plant near Dunhuang on the edge of China's Gobi Desert. Around a tall central tower stand roughly 12,000 mirrors. Each mirror slowly turns during the day so that its reflection continues to hit the same target near the top of the tower. Engineers call this kind of moving mirror a heliostat. The name sounds technical, but the idea is simple. It follows the sun while keeping the reflected light pointed at one place. One mirror adds only a thin beam. Thousands of mirrors, aimed together, create an intense concentration of light. From far away, the field appears to ripple because every mirror is sitting at a slightly different angle. Yet all of those reflections meet at the same target. That target is called the receiver. It is the bright section near the top of the tower, and it can look as though it is burning. Nothing there is actually on fire. The glow comes from sunlight being packed into a much smaller area. Inside the system, a special industrial salt is pumped through the receiver. This is not table salt, and it is not used as fuel. It is a liquid chosen because it can absorb a great deal of heat and carry that heat through pipes. After passing through the receiver, it can become hotter than 1000 degrees Fahrenheit or more than 500 degrees Celsius. The hot liquid then flows into a heavily insulated tank. At this point, the plant has collected energy from the sun, but it has not yet turned most of that energy into electricity. It has stored the energy as heat. That is the central trick behind the entire plant. A normal solar panel turns light directly into electricity. This mirror system takes a longer route. First, light becomes heat. The heat waits in a tank. Later, the plant turns that stored heat into electricity. The tank works like a giant thermal battery. A normal battery stores electrical energy through chemical reactions. This system stores energy as temperature. The hotter tank holds the energy collected during the day, while a cooler tank holds the liquid after much of that heat has been used. When electricity is needed, the hot salt passes beside water inside a piece of equipment that lets heat move between them without allowing the two liquids to mix. The water becomes steam. That steam spins a bladed wheel called a turbine, and the spinning turbine drives a generator that makes electricity. The cooler salt then returns to its first tank and waits to be heated again. So, although the shining mirror field looks futuristic, the final step is familiar. Electricity still comes from a spinning machine, much like it does in many traditional power stations. The difference is the source of the heat. Instead of burning coal or gas, the plant uses concentrated sunlight. At Dunhuang, the stored heat was designed to support about 11 hours of electricity generation. Some plants store less, while others have been designed to store heat for much longer. The exact number is not the main point. The important point is that solar energy collected around noon can still be useful in the evening, during the night, or early the next morning. That ability explains why anyone would build this complicated system when ordinary solar panels are already cheap and common. Solar panels are excellent at producing electricity during bright daylight, but electricity demand does not disappear when the sun goes down. In many places, demand remains high during the evening, when people return home, turn on lights, cook, cool buildings, and charge devices. A mirror and heat system can shift part of the day's solar energy into those later hours. The mirrors collect the energy. The tanks decide when it is released. The turbine controls how quickly it becomes electricity. That separation gives the plant something valuable: control over time. But the mirrors cannot work just anywhere. They need a very specific kind of sunlight. On a clear day, much of the sunlight reaches the ground in a strong, straight beam. On a cloudy or hazy day, more of that light is scattered through the sky and arrives from many directions. Ordinary solar panels can still use a good portion of scattered light. Mirrors have a harder time because scattered light cannot be aimed neatly at one small target. That is why dry regions with clear skies are so attractive. The Gobi Desert, Chile's Atacama Desert, North Africa, the Middle East, and the American Southwest often receive long periods of strong, direct sunlight. For a tower surrounded by mirrors, that kind of sunlight matters more than simply having warm weather. These plants also need space. The mirrors must spread across a wide area so they do not constantly block or shade one another. Each mirror also needs a clear view of the tower. Large, open landscapes make that arrangement easier. But deserts are not truly empty. They contain wildlife, fragile habitats, migration routes, cultural sites, and communities that may depend on the same land and water. A remote location can reduce conflicts with dense development, but it also creates new problems. Roads must reach the site. Replacement parts and workers may travel for hours. New power lines may be needed to carry electricity to distant cities. Then there is dust. A little dust on one household mirror is barely noticeable. A thin layer across thousands of precision mirrors can reduce the amount of light reaching the tower. After wind or a dust storm, large parts of the field may need inspection and cleaning. That creates an awkward trade-off. The driest places often provide the clearest sunlight, yet those same places may have very little water. The plant may need water to clean the mirrors, and the steam system may need cooling. Engineers can reduce water use with air-based cooling, but that approach can cost more and work less efficiently during extreme heat. So, a location that looks perfect on a sunlight map may look far less perfect once dust, water, roads, and power lines are included. The glowing tower also has to survive punishing conditions. Thousands of reflections must hit the receiver accurately. If too much light lands on one small area, that section can overheat. Every day, pipes and metal parts heat up, expand, cool down, and contract again. Over years, that repeated movement can wear equipment down. The salt creates another challenge. It must remain hot enough to stay liquid. If it cools too much, it can begin to harden inside pipes and equipment. Preventing that requires insulation, backup heating, careful monitoring, and experienced operators. The basic idea may sound simple, but operating it reliably is a major engineering task. This is the central trade-off of the mirror field. Its great strength comes from coordinating thousands of separate machines, but those thousands of machines must also be installed, aligned, cleaned, powered, checked, and repaired. So why not cover the same land with ordinary solar panels and add batteries? In many cases, that is exactly what developers do. Solar panels are inexpensive, quick to install, and easy to add in small or large numbers. Batteries respond almost instantly and can be used in far more locations. That is why mirror towers remain a specialized form of solar power rather than the standard choice. Their strongest advantage appears when a project needs large amounts of heat or many hours of electricity after sunset. Storing heat can be practical at a very large scale because adding more storage may mainly mean adding more hot liquid and building larger, insulated tanks. The plant does not need to produce all of its electricity at the same moment the sunlight arrives. A large hot tank also acts as a buffer. If a cloud briefly reduces the sunlight reaching the mirrors, the stored heat can continue feeding the turbine. The plant can deliver steadier output than a solar source that depends only on the light falling at that exact moment. This does not mean mirror towers will replace solar panels or batteries. A more practical future may combine them. Solar panels can provide inexpensive electricity during the day. Batteries can react quickly to sudden changes. A mirror field can collect heat for longer periods after sunset or provide high temperatures for industrial work. Each technology solves a different part of the problem. Some large energy projects are already combining multiple solar systems in the same development. The goal is not to prove that one technology defeats all the others. It is to use each one where it performs best. Researchers are also trying to run these systems at even higher temperatures. Hotter stored heat could produce more electricity from the same sunlight and could help power industrial processes that need intense heat. But hotter equipment also wears faster and can state more. These newer designs still have to prove that they can operate reliably for years. That final point is important. These mirror fields are visually spectacular because they make solar energy look almost physical. You can see the mirrors turning, you can see the tower glowing, you can point to the tanks where the day's heat is being held for later. But spectacular scale does not guarantee success. A good site needs several things at the same time: very strong direct sunlight, enough land, access to power lines, a workable plan for dust and water, reliable equipment, and a local electricity system that values power after sunset. Remove one of those conditions, and the shining field may no longer be worth building. So why are remote deserts being covered with massive arrays of what look like liquid mirrors? Because thousands of moving mirrors can gather direct sunlight, turn it into extreme heat, store that heat in liquid salt, and release it when electricity is needed, rather than only when the sun is shining. These mirrors are not trying to replace every other form of solar power. They are solving a narrower and more difficult problem: how to make sunlight wait. And that may be the most remarkable thing these shining fields produce: not only energy, but time. If you enjoy discovering the hidden engineering behind the technologies reshaping our world, subscribe to Parallax Depth. I'll see you in the next one.